Okay, so I wanted to continue with this work and energy, but we're going to add a new component now, the spring right here. Hopefully this doesn't get you shaken right here. So now we need to know what is the equation for springs. Well, here, let's assume we have a spring right here, and we have a special point for a spring. It's the unstretched or equilibrium point. That is, if you're not pulling or compressing it or anything, we call that the equilibrium point of the spring. That's the special spot. Now, suppose we were to pull this spring out a little way, some distance s right here. Then there's a force that wants to pull it back inward right here. And that strength of that force is proportional to this distance right here, this distance s right here. We could say it's proportional, or we could put in a constant, a proportionality constant, and call it k times s right here. Or k, we call it the spring constant. It's kind of the stiffness of the spring. If the spring is quite stiff, then it takes a lot of force to pull it a little distance right here. The units for that K are newtons per meter. It would be how many newtons do you have to apply to pull this out a whole meter. That's really what that K means right here. And for a spring, it's a constant. It's for that spring right there. Okay. This right here, this law, this is actually called Hooke's law. It's kind of strange that a guy called Hooke came up with the spring equation right there, so, but it is. This is back in Newton's time right here. Okay, so now our springs, first of all, they won't weigh anything. They can be stretched or compressed. The rule is the same. It's just that the force is in this direction. It's always trying to pull it back to your equilibrium position right here. Now we'll see that this is also going to be a conservative force right here. So that means it doesn't depend on how you got from point A to point B. You just take a snapshot of it at A and a snapshot of B, and the energy, or you don't care how it got from A to B. And we said anytime you're a conservative force, the work due to the spring is minus a change in potential to the spring. This is true for all conservative forces. It just so happens that the potential energy is 1/2 Ks squared. Now, I normally derive it, but I'm not going to derive it here. If you just couldn't remember it, you notice if you took the derivative of this with respect to s, what does that give you? Well, if you take the derivative of this with respect to s, it brings the 2 down, 2's cancel, and you get Ks, you get the force. We'll see that the derivative of the potential energy is the force. For potential energy due to gravity, it was mgh. If we take the derivative with respect to h, it's just mg right here. But s has got to always be measured from this point. You remember, for potential energy, we could call zero height anywhere we want. But for this, we have to call s equals 0 at the unstretched point of the spring, right there. Okay. Now you'll notice here that this is the first force that we've had that's not a constant. Our mg was constant, the normal, everything was constant. This depends on, as you pull this thing out, it's getting larger and larger. So if F is not a constant, A is not a constant. So we cannot use constant acceleration equations anytime you see a spring. Don't even think about it right here. So if you see a spring, you can use energy, you can use forces, but you can't use constant acceleration right here. Well, now what happens to our energy equation right here? Our energy equation then becomes, at least, remember we were looking at the case where the work due to friction and the work due to P were both 0. We'll bring that in later. Before, we just had the work due to gravity plus the kinetic equals the final gravity plus the final kinetic. But now, we're going to have work due to gravity plus U spring naught plus K naught equals U gravity final, U spring final, and K final. So the 3 questions we have to ask at each spot is, how high are you? Are you compressing or stretching a spring? How fast are you going? How high? Are you compressing or stretching a spring? And how fast? That's all we have to do at the 2 endpoints right here. So let's just say, here's an example right here. Suppose we have a block. It starts This is a smooth surface. Remember, we don't want friction in here. Smooth surface. We have a block sitting on this quarter circle right here. We start it from right here. We let it go. It slides down. Comes along here. Hits the spring. Compresses the spring a maximum distance, S. Right here, you notice it has to stop, because if it didn't stop, it'd still be compressing. It stops at maximum compression, and then it'd probably shoot it back right here, but we'll just go to that point right there. Okay, here is the unstretched point of the spring right there. So it stretched S from its unstretched right here. So the block starts from rest and slides down. What we want to find is how much does the spring get compressed, and what is the speed just before it hits the spring right there. So I'm going to call H equals 0, my lowest point right there. Remember, S equals 0 has to be the unstretched of the spring. And so we say, okay, at point, we're going to look at this between A and C. This is, our energy equation is between 2 points, between A and C. So you noticed right here, you've got potential energy. How high are you? That's quarter circle, so that's R up. So it's mgr. The spring, you're not even using the spring. You're way over here. Your speed is 0. Start from rest. So all of your energy at this point was just mgr. Down there, completely compressed, you have no gravity. You're down at H equals 0. You do have spring energy. It's 1/2 ks squared. The spring is compressed. It's the spring that has the energy, not the block right here. And then you stopped, so there's no kinetic. So all you have to do is set these two equal to each other. If you set these two equal to each other, you just throw the 2 up, throw the k down, and take the square root. You see how easy that is to work this complicated problem. If we'd had to do this with forces, this would be a mess right here. So you notice here it's one step. Now, if we wanted to look at it between A and B to get the speed at the bottom, again, the energies at A is still going to be the same. It's just mgr. These two are 0. But right there, you have no gravity. You have no spring. You haven't hit the spring yet. All you have is kinetic. And so you just have 1/2 mv bottom squared. Set these two equal. If we set those two equal, you can just get rid of the m's, throw the 2 over, and take the square root. So it's just 2 squared and 2gr. See how easy that is right there when you're using this equation. Okay, well, let's look at another case right here. Suppose we have a spring with a pulley with a mass right here. And let's say this spring is initially unstretched. So we're holding it up, the block up, and this spring is not stretched. Now, all of a sudden, we take our hand away. This thing is gravity. It's going to pull this down. It's going to stretch the spring here, and it's going to get some maximum stretching right here before this thing stops momentarily right there. And we want to find out what's the maximum distance this thing will drop right there. Okay. So if that's the lowest he goes, then his speed must be 0. So again, now if we look at the energy between this point and that point, I'm going to call H equals 0 the lowest spot. And so when you're right here, you have no kinetic, you have no spring energy, because we said the spring was originally unstretched. So all we have is potential energy, mg times your height, which is S. So there's all my original energy. Now when it gets all the way down here, it has no gravity because H equals 0. It has no speed because we said it stopped. So it's all went into spring energy, 1/2 ks squared. And the distance that dropped is the same S that one stretched. So I can just equate those two, cancel an S, multiply the 2 on the one side, and so you get S is just 2mg over k. So there's how much it would stretch. See how easy that these problems become one step almost right here. I could ask also, when you get down to this lowest spot, when you stop momentarily, I could ask, what is the acceleration of the block? Well, it's not 0. The velocity might be 0, but the acceleration isn't 0. Now, if I wanted to get the acceleration, I can't use work and energy. I have to use forces. At the very lowest point, all we have is what? We have mg down, and we have this spring force. Now we have to use Hooke's law, and we know how much it stretched, S, and so we know how large the force is at the very bottom. I'll call upward positive. It doesn't matter. But so what do we got? We got Ks minus mg equals ma, right? I can't assume a is 0 right there. So now I just have k times my s, plug in my s right there. K's drop out, and you just get 2mg minus mg, which is just mg. mg equals ma. Oh, a equals g, except I called that positive, so it's the acceleration is g this way, right here, at that lowest point. The next moment it's heading up. That's why its acceleration is this way, right here. So here we can see that this work energy, we add springs to it. We're not getting any more difficult right here. All we have to do, again, as long as these two are 0, is just ask, how high are you? Are you stretching and compressing a spring? And are you moving for all the parts at point A? And then do the same thing for part B and set the two equal right here. So don't make it a lot more difficult than it needs to be. Okay.